Let's do an example that shows how we can use power to analyze a circuit. Or in other words, we're going to analyze this circuit in terms of its power demands. By analyzing it, we want to find the current in each of these loads. We want to find the total current being delivered by the source. And we'll even find the complex power that source has got to drive. Alrighty. We have a source here with two loads in parallel. That's a pretty standard way of hooking up power equipment, where you'd have the same voltage going to a number of different loads. Each of these typically would represent a separate circuit in your distribution box. Generally speaking, in power types of systems, you won't hook them up in series, because in series you'd have a voltage division situation where you wouldn't be getting the full source voltage across the equipment. So this is pretty standard kind of a setup. Here we're told that our source is a 240 volt source, 240 cosine omega t. Unless specified otherwise, we're going to assume that the voltage rating there is in effective volts, so that this is 240 angle 0, where that is the RMS value. Anytime you're given 120 volts, 240, 277, 240, all of these are standard effective voltage ratings for different voltage, different standard voltages that are available from the power company. Alrighty, now you'll notice that, as we've said, the loads are not specified in terms of their impedance. You're not given a resistance and a reactance. You're given some sort of a power quantity and a power factor. Let's look first at load 1. Load 1, we're told, is a 1500 volt amp load with a 0.85 lagging power factor. Well, the fact that what they've given us is in terms of volt amps, that tells us that they have given us S, and in fact, the magnitude of S1 is equal to 1500 volt amps. We're told that the power factor associated with load 1 is 0.85 lagging. Well, power factor is equal to the cosine of the angle. Therefore, the angle or the phase of load 1 is equal to the arc cosine of the power factor, or the arc cosine of 0.85. We'll have to determine the sign here in just a second. But the arc cosine of 0.85 is equal to 31.78 degrees. So this is equal to it's equal to 31.78 degrees. Now the sine. We know that theta, the power factor angle, is equal to theta v minus theta I. We're told that it's lagging. Lagging refers to what the current is relative to the voltage. So this is saying that the current is behind the voltage, which means that theta I is going to be smaller than theta v, which means that theta will be positive. So we now know that S1 is equal to 1500 angle 31.78 degrees. I should have started out by saying that in order to get these currents, given the voltage and given the power, we can find the current directly if we know what the complex power of both of these loads are. Because we know that S is equal to phasor V effective, what a mess there, phasor V effective times phasor I effective conjugate. So we've been given a form of power. If we can get S, then we can write the current. The current is simply I effective is equal to S divided by V effective conjugate. So where we're going with this is, given the voltage, which frequently, generally speaking, you know, and given a load that's specified in power, we can calculate the current draw to the load, or by the load, by taking the complex power, dividing by the effective voltage, and conjugating it. So we've now got S1. Let's go ahead and calculate. Let's go ahead and get I1 from that. Then we'll look at load 2. So for load 1, continue on down here, we've got S, we know V, therefore I1 is going to equal S1, which is 1500 angle 31.78, divided by phasor V, which is 240 angle 0, and then we've got to conjugate it. And when you do that calculation, you get that I1 is equal to 6.25 angle negative 31.78 degrees. Now, it's time for a consistency check. We know that the current is lagging the voltage. We now have the current angle, or the phase of the current, it's not negative 31.78. Is that lagging the voltage? Yeah, the phase of the voltage is 0. This is negative 31.78, so it's 31.78 degrees behind the voltage, and at least that sign there is consistent with what we know. Now, while we're at it, let's just go ahead and calculate what the impedance of that load is. We don't need it, but just remind ourselves that that load really does have a resistance and a reactance. Let's calculate the impedance. Well, Z is, by definition, always has been and always will be the ratio of the phasor voltage to the phasor current. Doesn't matter whether it's effective or not, but since we're working with effectives, we'll use effective voltages here. We have then 240 angle 0 divided by the current, which is 6.25 angle negative 31.78 degrees, which turns out to be 38.64, 38.4, come on, 38.4 angle 31.78 degrees. Can you read that? 38.4, let's rewrite that, 38.4 angle 31.78 degrees. What I want you to see on this is, note the angle of the impedance. The angle of the impedance is 31.78 degrees, positive. Note the power factor angle, positive 31.78 degrees. In other words, the power factor angle is just the angle of the impedance. Alrighty, load 2. Load 2. We're told that load 2 is a 3,000 watt load. What are they giving us if they're specifying watts? Well, the units of average power, P, are watts. So what they've told us then is that P is equal to 3,000 watts. Now, we just saw that how, if we know what S is and we know V, then we can calculate the current associated with that. So let's determine the complex power S from the information they've given us here. Well, we know that S is a complex number. Let's just draw it on over here. S is a complex number that has a magnitude of S and an angle. And we know that P is the projection of S onto the real axis, and Q is the projection onto the imaginary axis. And that P then, P is equal to the magnitude of S times the cosine of theta. So if we know P, we can get the magnitude of S by simply dividing P by the cosine of theta, and we get then that the magnitude of S is equal to P, 3,000, divided by the cosine of theta, which is 0.9. Remember, the power factor is the cosine of theta. You can start to see why having the power factor, especially if you don't have access to a calculator that'll do trigonometric functions, which was the reality back several years ago, back when all this stuff was developed, rather than having trig tables and calculators, they just gave you the power factor. It was that number between 0 and 1 that derated or gave us the average or the real power from the complex power. So, magnitude of S then for load 2 is 33.33. And all we need now is the angle. Well, theta 2, this is S2. Theta 2 is going to equal the inverse cosine of the power factor, which was 0.9, and we'll determine the sign here in just a second. Well, the inverse cosine of 0.9 is 25.84. Now, is theta 2 positive or negative? How do we determine that? Leading means that the current is ahead of the voltage. That means that theta I is greater than theta V. That means that theta is negative. So we now have S2 is equal to 3333.33 angle negative 25.84. By the way, what are the units of S, magnitude of S? Volt amps. So we now have S2, and as we did for load 1, we can now calculate I1, or I2 rather. I2 is equal to S2 divided by V conjugate, which is equal to 3333.33 angle negative 25.84 divided by V, which was 240 angle 0. And we've got to conjugate that. And when we do so, we get that I2 is equal to, running out of room here, I2 is equal to 13.89 angle positive 25.84. Once again, we verify our signs. We know that this is a leading load, which means that I is the phase of I is ahead of the phase of V. Well, phase of I is positive 25.84. The angle V was 0. Sure enough, it's leading. And finally, let's just go ahead and calculate the impedance Z2. The impedance of Z2 is V divided by I2, which is 240. Let me just give it to you here. I2, we found, or I'm sorry, V is 240 volts. Let's write it here. Z2 is equal to phasor V divided by phasor I, which is 240 angle 0 divided by 13.89 angle 25.84, which gives us then Z of 17.28 angle negative 25.84. And once again, we see that the angle of the impedance is the power factor angle. So we now know I1, we know I2, we can now calculate the total current. The total current, I2, is simply equal to I1 plus I2, which from the previous page was I1 was 6.25 angle negative 31.78, and I2, add to it I2, 13.89 angle 25.84, and that gives us then the total, that's I total equals I1 plus I2, gives us a total current of 18.03 angle 8.81 degrees. So we had our source here, 240 angle 0, and the current coming from the source, I total then, is this 18.03 angle 8.81 degrees. Now that we know the total current, and we know the source driving that current, we can calculate the complex power S for the source. It's going to be phasor V effective times phasor I conjugate. Well, that's going to be phasor V is just the 240 angle 0 times the current from the source, which was 18.03 angle 8.81. That's got to be conjugated. And when we do that, we get then that the complex power associated with the source is 4327 angle negative 8.81 degrees. Negative 8.81 degrees. That means that theta of the source, which is equal to theta v of the source minus theta I of the source, it means that because that is negative, the current of the source is greater than the angle of the current associated with the source, coming from the source, is greater than the voltage of the source. And we knew that up here. That's consistent with what we know. The angle of the voltage at the source, it was 0. The angle of the current coming from the source was a positive 8.81 degrees, and so it's all self-consistent.